for whom the bell tolls, non-locality and randomness. So, Professor Dipankar Home.
Okay, good afternoon everyone, and as Urvashi has rightly mentioned, we should have scheduled my preceding talk to be the last talk. And now it's difficult to bring you back all to the mundane world of heart. And my talk is particularly and a bit unusual. So let me begin by remarking that I've followed the precept that the title of the talk is supposed to provoke curiosity. So it is notoriously vague, as I may say it. So that the caption is borrowed from, this is, you know, the title of a famous novel by Ernest Hemingway, and the famous poem where it says, "For whom the bell tolls, it tolls for thee." So I may give away the secret that is, here I take it that the bell tolls, the bell here is meant as a pun for Bell's theorem. So, and it is, I thought it would be highly significant, would be an understatement. It would be most relevant to talk about the significance of Bell's theorem at an occasion like this, because Bell's theorem, as Tony has described in various occasions, as the most abstract feature of science, so as one may say. And it is all the more very surprising and puzzling that it became also a tool for practical application, an invaluable tool. So how it came about, so that's a long story, but in my talk I will concentrate on a particular aspect in the context of the contemporary research scenario. It's more relevant, and we are also doing studies along that direction. And these are the two key words here. So as Bell's theorem has been described as one of the most profound discoveries of science, and it is a fascinating story how such an abstract theorem, such an abstract result, such a deep thought has become linked to hardcore applications. And Tony, in the course of his quite a number of visits to Calcutta during his lectures, I had asked him to choose the title of a talk in a very catchy way for the students. And talks he gave on Bell's theorem and quantum information, this is the title he had used in many of his talks, From Ethereal Abstraction to Hardcore Applications. And that is also the theme of my talk today. In the first half of my talk will be concentrated on some ethereal abstraction aspects of Bell's theorem, and then how they are linked to hardcore applications in a specific context. There are many contexts it has got linked, and these are some examples. This was original Bell's paper, and the titles of the papers are self-explanatory. So I've chosen it to give a chronological order. So after this Bell discovery, the various aspects of Bell's theorem and experimental tests, all these were done from foundational point of view. But the application of Bell's theorem, as one may say a hardcore application, this was the landmark paper which first pointed this out. And then this further consolidated that application. And then this was an application relatively recently pointed out, just 9 years old, and not yet, although in practical context it is being explored and it is being explored, and more plans are underway, as in the talk by Marcin Pawlowski. He mentioned about it. He just went through one slide mentioning Bell non-locality is being used for random number certification. But I will go deeper into that aspect and reveal what are the arguments, what is the fascinating logic behind it, and what are the potentialities therein. So this is in the context of this work. And first I come to some general aspects. So for that, the discussion of Bell's theorem has to be contextualized, and I choose the EPR Bohm scenario, what it is called, you are all aware of. And these are the measurement settings used by Alice and Bob. As I've denoted, these are the notational aspects, A-B outcomes. And now what is important, I give, Bell's theorem is discussed from various points of view. Here I present certain perspectives on Bell's theorem, which are then help us to get a holistic perspective linking Bell's theorem with the particular practical application I have in mind. So it is by no means to be complete discussion of Bell's theorem. It's the way. So one way of looking at Bell's theorem is that you consider Bell's theorem as a consequence of these two assumptions, and to put it very simply, if you could take any theory, you consider any theory which provides event by event objective descriptions, and then assign definite values to the individual properties independent of their measurement. And you talk about individual values of properties in either of the settings independent of what is done in the other in the other locality, in the other region. And this is what is known as the locality condition. And as Raphael in his talk has mentioned about the locality condition, this is where also it is assumed that it is space-time region. Whatever you are doing, the individual properties of the individual values of the properties are not affected by your choice of measurement setting in the other wing. But what is remarkable is these two are very abstract assumptions, but from these assumptions by simple algebra we can derive testable conditions, and the algebra in the most simplest form of Bell's theorem derivation, and that is quite instructive in the present context. If suppose I consider each pair and I define those quantities A1, B1, the outcomes level by small ab, and then for each pair by the first assumption I had invoked this assumption of realism in terms of definite values assigned to individual properties. It can be also called the assumption of objectivity. So one can say instead of local realist theory here, the assumption is made about local objective theory. Any such theory, for any such theory, you can define this condition for each pair of such EPR-Bohm entangled pair, and then you can go to the ensemble and get this inequality, and then so the violation, and then you can conclude that the violation of this inequality implies violation of local realism. So what is remarkable in this logic is that just if you experimentally violate this inequality, then it is not verifying quantum theory per se or anything. It goes beyond that. So that is the significance of Bell's theorem. It is not merely a new test of quantumness. Of course, Bell's inequality is as a tool for detecting entanglement, showing all other things, but that is the fundamental significance, and that will be particularly important in this new modern application I will be talking about. So this is an example where this deeper realization of a deep truth can also reveal facets about new applications. So now this same derivation of that inequality can be also viewed from a different perspective, and that is interesting. The seed for this was already sown in an old paper of 1987. In fact, this paper was preceded by the paper by Jarrett in a journal which is quite it has become quite obscure, the journal called News. Tony used that paper very much in his lectures. Physicists, yes. Physicists. So this journal is more easily accessible, so I've taken this reference, and this paper was written after that paper. So where it tried to view Bell inequality as a consequence of not those two assumptions, but from different set of assumptions, one of which was the assumption of signal locality, that is relativistic causality. Remember that the earlier locality condition I used was for the event by event description, so that is not testable by itself. So this approach I am talking about, and a further elaboration of this way of looking at Bell's theorem, and it is interesting these papers do not cite this paper. So this is an example how old things are also, but really these papers expand on what was the idea there. Perhaps they have done it independently, and now this is what is now commonly used for this application of Bell's theorem for randomness certification and all these things. So I'll go through the basis of the logic, why Bell's inequality has turned out so powerful in certifying genuine randomness. And there is some fundamental aspects involved in it, which in turn give rise to some deep fundamental questions. So there's a fascinating interplay between quantum foundational aspects and quantum information theoretic application. And this is beautifully illustrated in this way, in this recent line of study. Here I may again quote again quote something from Tony's writings, where he has referred to these recent developments as a reminder of the old interplay between thermodynamics and in the industrial revolution occurring in 19th century. The thermodynamic concepts, the precise formulation of those concepts had a considerable impact on the way the breakthroughs took place in the industrial revolution. So there was an interplay between those developments of Carnot engine and so on, and the basic thermodynamic principles. So here also we have in this form an interplay between the quantum information technologies and the foundational aspects of quantum mechanics. Now this is framed that here we go to there it was Bell's inequality was derived from assumptions made at an event by event level, which were in itself not at a statistical level. Then you go to the statistics. Here you assume that if each state of the EPR pair is prepared by a reproducible procedure, which you denote by kappa, then suppose we have a theory which can predict with certainty the outcomes of all possible measurements performed on it. That is, we assume a perfectly predictable theory which is able to reproduce all the outcomes for the EPR-Bohm pair. Suppose such a theory exists. And along with that assumption, we impose the no signaling condition, which is relativistic causality principle. So then it is interesting that from these two assumptions also, it is possible to derive the Bell inequality. And that form of Bell inequality, it goes in terms of probabilities, that the measurement statistics of the outcomes corresponding to the measurements, you have these joint probabilities. And of course, we know this condition that the sum of the joint probabilities should be 1. And then if you impose the predictability condition, that means the joint probability of outcomes should be either 0 or 1. That means for any definite run, you know the outcome definitely. So either it will occur with probability 1 or it will not occur. So the joint probability would be either 0 or 1. And also because of the no signaling condition, the probability of the occurrence of outcome in one wing should be independent of the setting of the other wing. So you see, these are the two possible settings. So the probability of obtaining this outcome is independent of the setting here. So we can write it in this form, and similarly for this form. These are the outcomes and these are the settings, and this is the state preparation procedure. You each time go through the same state preparation procedure. Then the theory should satisfy both these conditions. So for such a theory, then by just using the properties of the probability distributions, the general properties that the sum of all the probabilities should be 1, and that the predictability condition implies that it is either 0 or 1, one can show that the marginal probability should be either 0 or 1. And then one can show that the joint probability, and this is important, this joint probability can be written in the factorizable form. So this just follows by just assumptions, the general conditions that a physical probability distribution should satisfy. So it is just a consequence of those two assumptions. And then if you get the factorizability condition at this stage, where you have used the predictability condition and the no signaling condition at this stage. So then you get the factorizability condition. And now once you get the factorizability condition, then one can show that Bell inequality follows. That is known as the Bell CHS form of the inequality, and this Bell CHS form of the inequality is this form, combination of correlation function, and each correlation function can be written as sum of joint probabilities. And if these joint probabilities are factorizable, one can show that this inequality is satisfied for probabilities just being positive definite and sum of all probabilities to be 1. So the message from this exercise is that if you accept the validity of the signal locality condition, which we all believe to be true, then the empirical observation of the violation of Bell inequality means violation of the predictability condition. That means there can be no theory of nature that can predict with certainty the outcomes with a well-defined states preparation procedure specified by the theory. So that means perfect predictability of physical phenomena must be impossible, and this is independent of quantum theory. And that is a wonderful realization, a deep realization of the power of Bell inequality. So what we learn is that Bell inequality, the validation of Bell inequality, can come in two different ways. One is that event by event objective descriptions, and this description, I hear a bit more technical term for those who know the literature on foundational aspects of quantum mechanics. This event by event description, there are concrete models, and when one uses what is known as ontic, or more popularly hidden variables, that is auxiliary variables apart from the wave function, and those variables are used to provide event by event description, which you cannot provide in terms of wave function. But those details are not important. There are specific models of that kind which was showed that you can provide event by event description of quantum phenomena using such auxiliary variables, which are called ontological variables or hidden variables, in the sense that the variables are assumed to be giving objective values of properties, which are, whether they are knowable or controllable is an open question, it's not specified. So if you just assume, here the details are not important, here if I just assume such variables exist and it is possible to provide such descriptions, then you have Bell inequality following. And on the other hand, you can get Bell inequality from the conjunction of these two conditions. Then violation of Bell inequality, what does it mean? That either this objective description at event by event objective description or realist description at the ontic level has to be non-local. This phrase is non-locality here means at the level of this event by event objective level, not the, so one has to distinguish signal locality from it. So loosely when we say quantum theory is non-local, one has to be careful. It is non-local means that it violates the locality condition which is assumed at event by event level for assuming that ontic variables or it can provide objective description of it. But if you assume signal locality at the operational level, which is the statistical level, that derivation I gave of Bell. So it is Bell inequality you can derive from the event by event assumptions or at the assumptions at the conditions at the operational level, and then you get this consequence that measurement outcomes are fundamentally unpredictable. Now we have examples of specific ontic or hidden variable models of such non-locality, but then the question comes, how do you reconcile such non-locality with signal locality at the statistical level? If you have event by event non-locality where events are specified in terms of ontic variables or hidden variables, then so it means this implies that these ontic variables have to be necessarily unknowable or uncontrollable. Remember, in this derivation, we have assumed that you derive Bell inequality assuming that a reproducible state preparation procedure can produce the joint state over and again. So that assumption we have made that the probability is 0 or 1 can be verified with respect to such a theory, because you can operationally verify that assumption. So if you assume such a theory exists and you have verified, then Bell inequality is a consequence of such a theory. Now what does it enable us to say? That if in nature you see that Bell inequality is violated, it means that such a theory cannot exist in nature. That means no matter how clever you are, no matter how many ontic variables you add, you cannot give a predictable description or perfectly predictable description. Because that would have been an open question. It depends on how smart you are, as Pawlowski in his talk was saying, when we assume security, it always depends upon you assume how smart. But it is not a question of how smart you are. It is in nature, when you empirically verify this thing violation, it tells that God does play dice at a fundamental level. You cannot have such thing. Now that provides that realization provides that this violation of Bell inequality provides a powerful tool to produce really what we may call genuine randomness. Otherwise, randomness specifying or genuine randomness is an open problem. You can never in that sense certify, because you can never be sure whether one can add more and more variables and predict any phenomena with certainty. Like we say, the meteorological things, if you have known everything, coin tossing. So if you design carefully, you know all the conditions, you could have predicted. But here that statement even cannot be made. So it is independent of the computational power or independent of power of any adversary you can think of. So this is very powerful, as this certification of genuine randomness has been an open problem, and this randomness has, and certification and quantification has such wide-ranging applications, as you all know. Now to put it in perspective, at the moment we have different types of random number generator, but see that what Pawlowski talked about, they have been all using is what we may call pseudo-random number generator, where computer-generated algorithms are used to process the initial random seed. You have an initial random seed. How do you produce that initial? You produce by writing a clever algorithm which ensures it to be reasonably random against the power of. So it makes assumptions, the random character, and based on assumptions about the computational power of adversary. So there can be always in principle an adversary having more computational power which can crack this pseudo-random number generator. So for certifying genuine randomness, one requires unpredictability by any observer independent of its computational power. This is what that logic ensures, that Bell's violation would ensure. But there are, other hand, what has been called in the literature true random number generators, which are used for various important purposes, crucial purposes, security purposes, where they exploit complexity of physical processes like meteorological fluctuations or stellar events, solar as supernova things, which Pawlowski also mentioned, Marcin mentioned. That is what they have been. This is a higher level random number generators. And then there are, of course, now quantum random number generator. But it is important to realize that this quantum random number generators are based on the postulated inherentness of the irreducible statistical feature of quantum mechanics. That means it assumes that quantum mechanical predictions cannot be modeled by any deeper theory, even by event theory. But we already know there are quantum mechanical phenomena which you can reproduce by these underlying theories using ontic variables or hidden variables, though they may have non-local character. So this is an assumption. So to avoid that assumption, one needs what is called the genuine random number generators, and these genuine random number generators are based on the violation of Bell inequality, because it guarantees the unpredictability, genuine unpredictability of measurement outcomes. So that is what I have come to. Now I come, so that once that is realized, then the question comes that does larger amount of violation of Bell's CHS inequality necessarily imply increased amount of randomness? This is important for the practical application, and also from the fundamental point of view, this question is important. It shows, so non-locality is a resource. Non-locality gives rise to randomness. Now when we say that, like statements like this which are made, one is to understand the full import of it carefully. Non-locality is necessary for certifying randomness, but unless we address this question, we cannot clearly, unambiguously say the relationship between randomness and non-locality. Means what is the real resource of randomness, the amount of quantitative resource of randomness. Like quantum entanglement is used as a resource for many information theoretic tasks. For entanglement is necessary for many of these tasks, but the amount of entanglement may not be always related to the fidelity of the task in a monotonic way. So this is a question which is of critical importance, because in application, when you start with a resource, we need this sort of fidelity. Then whether the resource with more entanglement, less, which one will be important. So here also it will be important to generate a random number generator, to get a genuine random number generator which is dependable as well as efficient. Well, the dependability part we ensure by violation of Bell inequality. Now the efficiency part of that genuine random number generator would depend upon our knowledge about how the amount of violation of Bell inequality is related to the amount of certified randomness. This is, in that context, this question is about, because it is not enough to just certify randomness, you have to also know it quantitatively how much random it is. So for that, this relationship has to be analyzed, and this relationship studies, this analysis of this relationship has not yet been well explored. I shall just briefly, since I have now 5 minutes more, so I am not going through the basic, just may remark that there are well-defined procedures for quantifying randomness, and so the amount of uncertainty, this randomness is defined in terms of minimum entropy, this quantity. It is the maximum probability, it is the maximum value of the probability of the occurrence of an outcome, which defines minimum entropy, which is taken as the measure of randomness. In the worst case, there are other measures you can take, and then you can define amount of randomness in terms of bits. And then in the Bell CHS scenario also you can define, because if you certify randomness in terms of these outcomes which violate Bell CHS, so you have to talk about the joint probability distributions of these outcomes, and in terms of that randomness can be quantified, and you can define upper bound of this genuine randomness and lower bound of randomness. And what has been explored so far, and that this is the pioneering paper in this subject, this quantification part, and where they studied the relationship between the lower bound of genuine randomness and the violation of Bell inequality, and it was found to be monotonically related, means higher violation implies. But then came this study by Asin et al., where they showed that the upper bound of genuine randomness can be, whose maximum possible value is 2 bits for the EPR-Bohm case, and this can be achieved for choice of settings for which the amount of Bell violation is very small. So this surprising result, not surprising, this very stimulating result, I shall be agnostic, so we have to probe more deeper to say whether it is surprising. So this stimulating result, that it's small amount of non-locality, calls for further studies, and that is an area we are also looking into. So these are the open questions, and the study of these questions is important for developing what we may call the resource theory of randomness. This is from the application point of view for more efficient application uses of what we may call genuine random number generators, because this is the new generation of random numbers to be widely used in global communication networks, which Pawlowski talked about, and also for understanding the interplay between non-locality and randomness. So this is the fundamental foundational aspects, the foundation. So this is a fascinating interplay between. This is an example of how closely linked the foundational studies with quantum information applications. And already we have some results. I shall just 2 or 3 minutes, just to give the flavor of the interplay again, how the foundations. So how to get more randomness, or this, to throw more light. There has been a very interesting foundational study by GSA group, and then followed by a very illuminating experiment by Quet in 2001, where amidst other things they demonstrated what may be called the phenomenon of hidden non-locality involving local filtering. I'm not going into the details. The message is you can start with a local state, a state satisfying, and the way appropriate filtering of states using an experimental scheme, one can show non-locality. Now this experimental scheme, if one applies in the context of extracting randomness, what we have found that it is that with you can study, this is the experimental procedure which has been used to investigate hidden non-locality, but our proposal is to use that in the context of randomness study, and then one gets powerful results that even using mixed states and pure non-maximally entangled states, one can get maximum amount of randomness, which one can get only for pure maximally entangled states. And then applying to different types of mixtures and general class of states, one gets the result that for any all class states, there are situations where the maximum value of randomness can get decreased, but the Bell violation can get increased. So this indicates what we call quantitative incommensurability between the amount of upper bound of genuine randomness and violation of Bell inequality. This is a new result whose implications and further ramifications need to be looked into from both application and foundational point of view. And in all the case studies, this is interesting, one can get close to 2 bits of genuine. That means you can get quite an efficient random number generator if you use that sort of setup and start with any input state, which may not be pure maximally, which is hard to prepare in practice. So it may have useful practical applications. So this the use of local filtering technique in the context of random number generators, that is the new perspective that has evolved from this study we have been making, and we'll explore it. And this not only brings out that do not behave monotonically with each other, but this for pure and mixed entangles. So I conclude with these remarks. So we all know. So what I stressed, what we need to have is dependable and efficient, whose importance was well highlighted by Pawlowski in his talk in the context of those big projects of quantum communication. And and for that purpose, the relationship between randomness and non-locality need to be explored. Thanking you all.
Any questions?
This is a rather obvious question, which I'm sure must have been explored, but do you gain anything by simply replacing CHSH by GHZ?
By
GHZ.
in fact, these are whole set of questions not yet thoroughly investigated. Hardy has been explored. But GHZ is 3-party, no?
Yeah.
Yes, so